Okay, start recording now. So we have les équations paramétriques suivantes. On a x égale à exponentielle de oméga t, cosinus oméga t, y égale à exponentielle de oméga t, sinus oméga t, and z égale exponentielle oméga t. A et omega sont de constantes positives. So you should notice A and omega are positive constants. So the first question is, exprimer les coordonnées cylindriques ρ, phi et z du point M en fonction du temps. Exprimer les coordonnées cylindriques ρ, phi, z du point M en fonction du temps. So you see here they've given us x, y, z. This is like from the coordinate Cartesian, x, y, z. Now what they're asking us to find now are the expressions of the coordinate cylindric ρ, phi, z. So if you remember very well, when we're looking at coordinate systems, there's a part or a sub-chapter that we did where we were forming expressions for migrating from one coordinate system to another coordinate system. I remember we came up with expressions for ρ in terms of x, y, z, and we came up with expressions for the inverse when you're moving from the cylindric going into the Cartesian plane. So now here what they're asking us is to go from the Cartesian plane into the cylindric plane. So you use these parameters that we have here, the x, y, and z. You use them to find the expressions for ρ, phi, and z. You have the formulas in your polycopies. So when we go to the polycopy, okay, I haven't opened it. Let me just open the polycopy. We're going to use, it's this one. So just to show you that you have the stuff, and mostly mechanics exercises just like this. You'll be using the formulas that you have with you in your polycopies. So I showed you guys how to calculate these things here. You remember, not so?
Oui.
Okay, so we have x égale rho cos phi, y égale rho sinus phi, z égale z. But what we are looking for now are these three here, rho, phi, and z. So we have the formula for rho égale racine de x carré plus y carré, et on a phi égale arc tangent de y sur x, and we have z, z ne change pas, c'est toujours la même chose. So we have these expressions here, and these are the formulas we're going to use. You see that it's direct from here because you already have x given in the question and you have y given in the question. So you just square the expression for x, square the expression for y, add them, you square root, you get your answer. This time you just say arctangent to get your y, you put it over your x, you simplify the expression, you calculate the arctangent, it's safe. So we go back to the question. So we have our x, we have our y, we have our z. So we know rho, first we calculate rho, we know rho is equal to racine de x carré plus y carré. So when I come to the solutions are here. Yeah, so we have this here. So we first calculate rho, rho being equal to racine of x carré plus y carré. So we know x is equal to this here. And this is what I've written here, and I've squared it. And y is equal to that there, which is what I've written here, and I've squared it. Then now we go into simplification. When you square this, you have a exponential omega t, le tout au carré. You square all of it, and cosinus squared plus a exponential omega t squared sinus squared omega t. So we know that the a omega, sorry, not a omega, but a exponential omega t is a common term. It's common there and it's common there. So we can factor it out. And this is what I did here. I factored the a exponential omega t au carré, and it gave me that, and I had this left now, the cosinus carré omega t plus sinus carré omega t. And from trigonometry, we know that this is equal to 1. So this will give us 1, and what's going to be left is a exponential omega t au carré. Then the carré and the racine carré will simplify there, and we'll just be left with a exponential omega t as our rho. So rho is equal to A exponential omega t. Is that one clear?
Oui, c'est clair.
Okay, lovely. Then we're going to calculate phi now, and we know the formula for phi is equal to arc tangent y over x. So we are going to say arctan, y is r exponential omega t sinus omega t there in the numerator, x equal r exponential omega t cosinus omega t there in the denominator. And again, the r exponential omega t is a common term in the numerator and the denominator, so it will simplify. Yeah, it's going to cancel out and we'll be left with sinus omega t over cos omega t. Sinus omega t over cos omega t is equal to tangent omega t, that we know. Sin x over cos x is equal to tan x. So when you have sin omega t over cos omega t, it's going to give you tan omega t. Then we have arctan of tangent omega t. And I told you that arctan is tan inverse. So we have tan inverse of tan. It's going to cancel out. So we'll just be left with omega t. It's like the tan inverse and the tan are going to simplify each other. So what's just going to be left is omega t. So our phi is going to be equal to omega t as that. And z, as I told you before, in the coordinate Cartesian and the coordinate cylindric, the z is the same thing. It does not change. So z is still going to be exponentielle omega t. Et voilà les expressions rho, phi et z dans le coordonate cylindric. We have their expressions in terms of t, as the question was asking us, okay? They said exprimer les coordonnées cylindriques rho, phi, z du point M en fonction du temps. So we have our expressions there that I've boxed. There they are. Is that clear?
Oui, c'est clair.
Oui, c'est clair.
Lovely. So we go to 1b. Now 1b, they're saying, écrire l'expression du rayon vecteur OM dans la base cylindrique. So this we did again. We formed or we found the expression for OM dans la base cylindrique. Does someone remember how you write OM dans la base cylindrique? Anyone?
OM is equal to OM prime plus M prime M.
Yeah, and then the final expression in terms of these guys that we found, the parameters in the base cylindric.
It's rho in the direction of E rho, Z in the direction of K.
Exactly, correct. That's very nice. It's OM égale rho suivant E rho plus Z suivant K. So these things, are supposed to know them. I don't know if I emphasized this last week. You're supposed to know them by heart. Okay, the OM vector vitesse and acceleration. The vector vitesse and the acceleration, it's not necessary that you know them by heart. You just know them by heart because it simplifies. Oh, it gives you more time. It saves you time instead of deriving OM every time to get the vitesse. It's better you just know the formula or the expression for the vitesse in each coordinate system, so that in the exam you don't have to start deriving OM. But for OM, you have to know it by heart. So when we tell you OM dans la base cylindrique is equal to what? You have to know it. OM dans la base sphérique is equal to what? You have to know it. OM dans la base cartesian is equal to what? You are supposed to know it, as you've seen. So imagine you are in an exam here and they tell you write the expression for OM dans la base cylindrique. You do not have a polycopy to check from. So it means you have to commit it to memory. So as our friend has told us, OM is equal to rho, E rho plus ZK. So we are going to write it as rho, E rho plus ZK. So you see rho, E rho plus ZK. But we have found the expression for rho and we have the expression for z. So we are going to substitute these values we found there and there in this thing and get our expression for OM. So when we substitute a rho with its value there, we're going to have A exponentielle oméga t suivant E rho plus exponentielle oméga t suivant K. If you want, you can leave it there. If you want, you can factorize the exponential omega t, and you have entre parenthèses A E rho plus K. That's it. But they're both correct. So your OM, voila, your OM is there, and that's your expression for OM. Then the next question is now saying, that's 2A, calculer en coordonnées cylindriques le vecteur vitesse du point M. Okay? Calculer en coordonnées cylindriques le vecteur vitesse du point M. So for this question, there's a lot of ways you can attack it. Okay? If you want, you can just get this OM here, this OM, and differentiate it. You just say the OM dt, you differentiate this one, or you can use the formula that's in your polycopy for the vitesse, vector vitesse. This is why I told you it saves you time. So if you know the formula from your polycopy, you just write it down. For example, the formula is here, vitesse dans la base cylindrique, c'est rho point E rho plus rho phi point E phi plus Z point K. So this is your expression from the polycopy. So you can just write it like that, and then you start substituting. Rho point, you can calculate, it's easy. Rho, you write it. Phi point, you can write it. Z point, it's just comme ça, and you have your expression. So we are not going to differentiate this directly. We are going to use the formula. So we know the formula is this one here. You have it in your notes. And now we just need the values for rho point. We have rho being equal to A exponentielle omega t. So if I derive a rho par rapport au temps, because rho point is the rho dt, is going to be equal to. You guys know how to derive the exponential function, n'est-ce pas?
Si.
Okay, good. So when you're deriving the exponential function, for those of you that are maybe feeling shy to say I don't know, you differentiate the exponent. Okay, sorry to say exponent since we're saying exponential function. Yeah, but it's called the exponent though, but I would say the power so that you can understand well. You differentiate the power. So in this case, the power is omega t. So you differentiate the power and then you multiply the derivative that you're going to get from differentiating the power by the entire expression that you have. So when we're differentiating this one, we'll differentiate omega t, first of all, par rapport au temps. And when we derive omega t with respect to time, it's going to give us omega. Okay, so it's going to give us omega, and then we multiply that omega by the entire expression. So we multiply omega by this entire expression, it's going to give us A omega exponential omega t. And this is going to be a rho point. Then we have phi point there. Phi point, we said phi was equal to omega t. So when you derive omega t par rapport au temps, it's just going to give you omega. And then z point, z égale exponential omega t. So we derive this par rapport au temps. We'll be deriving the power there. It's going to give us t. It's going to give us omega. Then we multiply omega by the entire expression. It will be omega exponential omega t. So what's left now is just to substitute these values into the expression that we have for the vitesse. So rho point, we'll write A omega exponential omega t, suivant E rho, like that. Then this one we have rho phi point. So we just write rho. Rho is equal to A exponential omega t fois omega, there the phi point, and it's going to be this there. And finally, z point is omega exponential omega t. So we're going to write omega exponential omega t suivant k. And just to simplify your expression a little, you can factorize omega exponential omega t because it's a common term. So when we factorize omega exponential omega t, is going to be equal to omega exponential omega t between brackets A E rho plus A E phi plus k. And that's going to be your vector vitesse, like that. Is it clear? It's just clear.
Oui.
is saying repeat. Your connection is bad. I didn't get you, but I heard you say repeat.
And the
Okay, so
exponential.
how to derive the exponent? Okay, I think she's saying on the exponential part. So here we're deriving the exponential function. So normally the formula for the dérivé of the exponential function, si vous avez e à la puissance f de x, okay, we have exponential of f de x. The derivé is going to be f prime of x multiplied by exponential of f de x. What this is telling us is you derive the power, what the exponent has been raised to, what the e there has been raised to. You derive it, and then after you derive it, the answer you get from deriving that power, you multiply that answer throughout. Yeah, you multiply your entire expression by that. So here they're asking us to say we're deriving exponential omega t. So what we're going to do first is we're going to derive the omega t. When you derive the omega t, par rapport au temps, this t is going to go. So we're just going to remain with the omega. And what we're going to do now is we're going to multiply the entire expression there by omega that we've gotten from deriving the exponent there. And it's going to be r omega exponential omega t. And that's how you derive the exponent. Is it clear?
Yes.
Okay, I think that was a yes. Your your internet the internet connection is poor, so can't really get what you're saying. Okay, it's clear. Great. So we advance. We
I have a question.
advance. Okay.
Yeah, so does it mean when we derive, we find the derivative of OM, the answer must be the Vitesse, the one
Yes.
you're finding?
Yes. C'est tout à fait ça. Exactement ça.
All right, all right.
Yeah. So as I told you, there's two ways you can do it. So if you had to derive this expression here directly, without using the formula there, you just derive this directly, you'll get the same answer. You'll get this here. As if you do the correct thing. Okay, so now the next question is, on déduit le vecteur tangent. So now, we've worked a little in the coordinate cylindric. Now what's happened is, we're moving from cylindric now, we're going to le coordonate freinet, le repère freinet, okay? Because we're now dealing with vector tangent. This one is found in le repère freinet. So switch your minds now, go into repère freinet et rappelez-vous des formules ou bien des expressions qui se trouvent dans le repère freinet. All these things, you have them in your notes. The vector tangent. So they're telling us now, what I want to find is a vector tangent. So the solutions begin by saying, on sait que, yeah, and I'm sure you've been taught this in analyse or algebra, whatever modules. When you're answering, normalize using expressions like on sait que, donc, et, on suppose, on pose. You know, write some notes in your workings. Don't just write expressions and formulas and all that stuff. Explain. We're going from here to here. We're going to begin from here. We're going to do this because we need this. That's how you solve. It might not be clear in the solutions here because when we're copying solutions in class, we just copy them quickly because it's tiring. But in the exam, you have to explain. So we begin with, on sait que, so you have this formula also in your notes. If you just go to the coordonate freinet, you will find it. It's saying, la vitesse du point M dans R égale d de S dt, la dérivée de l'abscisse Keveling par rapport au temps fois le vecteur tangent. Okay, and then we know again from the notes, you will find all these things that ds dt is equal to module of v. It's there in your notes. This is nothing new. It's there in your notes. And so if this is equal to V, and we can replace module de V there, module de V, we can replace it there where there's the S dt. And if we just change the subject to a formula, we make T subject, is going to give us T equal to le vecteur vitesse divisé par le module du vecteur vitesse, like this. So vector vitesse, we have it, it's there. What's just left for us to calculate there? The module of the vector vitesse, and we are going to get our tangent. You see how easy it is? Just formulas. So when we come to this polycopy, they are cinematic. We go to the vector vitesse. It's this one here. So we found our vector vitesse as that, and the module is also there in the formulas or in the polycopy. It's a square root of rho point carré plus rho phi point carré plus z point carré as your formula for the vector vitesse, which is this one here, which I've written here, rho point carré plus supposed to be rho phi point carré plus z point au carré. Then we calculated rho point is there, you just square it. Then the next one is rho phi point carré, which is this term here. And then finally we have z point carré is that term there. So they are like this. This is rho point carré or rho phi point carré plus z point carré. When you square these guys, you square them, you have a squared omega squared exponential squared omega t plus same thing there plus omega squared exponential squared whatsoever. So from this, you see that the omega and the omega squared and the exponential squared omega t are common terms. So you can factor those two out, okay? So when you factor those out, you have a plus, it will be a squared plus 1, because this entire term will be factored out. And then when you square root that term that you factored out, the omega squared exponential squared omega t, when you factor it out, the squared is going to simplify with the square root there, and it's going to just come out as omega exponential omega t. It's a bit confusing since I'm just explaining by word of mouth. Sit down and try to simplify this with a pen and paper. You will see how easy they are. So when you factor out this guy, what's going to remain in the square root now is going to be 2a squared plus 1. And this becomes our V, module de vector vitesse. You just call it V. It's going to be omega exponential omega t square root of 2a plus 1. Maybe some of you might be wondering, where has this come from? It's just a simplification of this. I'm sure all of you know how to work out square roots and squares, surds, and all that stuff. So if you just sit down with a pen and paper, you try to simplify this, you arrive at that, and that's going to be your module de V. And finally, we can simplify our expression for T, the vector tangent, which is vector vitesse being this one over the module de V, which is that one there. And as you can see already, we have omega exponential omega t in the numerator and omega exponential omega t in the denominator. So they'll simplify these guys, and what's going to be left is this term in the brackets and this term this side here. So it's going to be vecteur tangent t égale a suivant e rho plus a suivant e phi plus k over square root of 2a squared plus 1. Is that clear?
Oui.
It's simple stuff, not so?
Oui, c'est clair.
Okay. So next question. In the next question, they're asking us to, it's question 3. They're saying, déterminer l'abscisse Kevlin S de phi du point M, sachant que phi is equal to 0 lorsque S de phi equal to 0. Okay, so phi is equal to 0 lorsque S de phi is equal to 0. We're supposed to calculate l'abscisse Kevlin en fonction de phi. L'abscisse Kevlin en fonction de phi. So we begin our solution by saying, ona S elapsis Kevlin, okay? And as we saw from up here and from our notes, the S dt is equal to module of vecteur vitesse. That's what we've written here. The S dt is equal to V. V, c'est le module du vecteur vitesse. And vector, le module du vecteur vitesse, we have it as that there, which we calculated here. Omega exponentielle omega t racine over 2a carré plus 1, that there. So now we just do some simplifications here and there. So we want ds. Sorry, not ds, we want s, but we have ds. So what are we supposed to do? We're supposed to integrate. Okay, we're supposed to integrate the ds par rapport au temps for us to go to s. It's just the opposite. When you're moving from s to the derivative, you derive it to get the su dt. So now going from the s dt to s, you have to integrate the s dt par rapport au temps, and that's what we're going to do. So we have the s, when we just multiply this dt this side, it's going to be the s equal to v dt. Then from here, we'll need to integrate this side and integrate on the other side, and we'll have our s. But look at the question. The question is saying s de phi, not s de t, but s de phi. So we'll have to work in terms of phi. So we'll do a little changement de variable. It's very easy stuff. From the question from up here, we found that phi point equal to omega t. Phi point was equal to omega, sorry, not phi point, but phi was equal to omega t. Je m'excuse pour ça. Phi is equal to omega t. This expression I boxed here. Phi is equal to omega t. So we use that now to do this changement de variable. Since our expression has been given in terms of t, and they're asking us in the question to work in terms of phi. So now we'll change the variable from t to phi. So we need to find an expression in the question or in our solutions that's linking phi and t, and then we'll change the subject there and replace every t by phi. Changement de variable. You'll be doing it a lot, especially in analyse. Changement de variable. So we have phi equal to omega t. So if
Can you just repeat what you just from saying about changing the variable?
Okay, so in the question, when you look at the question, they are saying déterminer l'abscisse Kevlin S de phi, okay? And even the initial conditions that they have given us, they are phis. It's like phi is equal to 0 when S de phi is equal to 0. So in their question, in the question, they're asking us to find S in terms of phi. But when you look at the expressions that we've been working with so far, they are all expressed in terms of t. Okay, so for us to get our answer for s in terms of phi, as the question is asking us, we're going to have to change the variable from t, which we have now, to s, which they are asking us to use. Okay, so that's why I said we're going to use un changement de variable. We call it changement de variable, where you have to change the variable from one thing to another, depending on what you're looking for. Here it's because we've been asked to work with phi, that's why we're going to have to change the variable. So now what we're going to do is we're going to look for an expression in the question or in our solutions that we've been working with so far that's linking the two variables so that we can change the subject there and replace the old variable by the new variable that we want. So we have phi and t as the variables constant here. So we need to find an expression that's linking phi and t. That's why we went up here. At the very beginning, we found that phi was equal to omega t. Phi is equal to omega t. So we can use this expression here to change the variable, okay? So phi is equal to omega t. And here we have the s is equal to v dt, okay? But we don't want to have dt here, we want to have d phi. So what we're going to do is we're going to derive this side and we're going to derive this side. So we introduce, when we say d de phi, even this side we'll put and d, omega is constant, so it's just going to be phi is equal to omega dt, like this. When we introduce d on one side and d on the other, like the differential on one side and differential on the other side, it's going to be d phi equal to omega dt. And from here now, we can change the subject. We say dt is equal to d phi over omega. Like here, it's just divided by omega, you divide by omega. dt will be equal to d phi over omega. So here where there's dt now, we can just put our new expression there. So dt, we replace it with d phi omega. And then when you substitute your expression for v, there, here where there's v, you put your v. V is equal to omega exponentielle omega t, racine 2a carré plus 1. Now, omega t is equal to what? From this thing here, we see that omega t is equal to phi. So there where there's omega t, I can replace it with phi, okay? And my expression now is going to become this. Because this is a constant, I can take it out of my integral. It's just going to be disturbing me. Can take it out. I'm sure we all know how to integrate, hopefully. So I can take this out of my integral. It's going to be square root of 2a squared plus 1. Then we have the integral of e phi and the phi this side. From here, it's simple. We're integrating e à la puissance phi de phi. What's the integral of e phi? De phi. This is the magic of the exponent. When you have like the exponential x, l'integral de l'exponentiel de x dx, it's just equal to e dx. It does not change. It's like when you derive e dx, like d de ex dx, it still gives you e dx. That means when you integrate it, it's still going to give you the same thing. Okay. So here when we integrate exponential de phi, it's just going to, it's still going to be e phi like that, plus c, the constant of the integral. Sure, we remember this part also. So it's going to be square root of 2a squared plus 1 exponential of phi plus c. Okay, so now they give us the initial conditions in the questions to help us find the value of c. So they told us that phi is equal to 0 when s of phi is equal to 0. Okay, s of phi is equal to 0 when phi is equal to 0. I swapped them, sorry. So we have s de phi equal to this plus c equal to 0, because phi is equal to 0, so this is going to be 1, so it's going to disappear. It's going to be exponential of 0, which is 1, so we can just ignore it for now. So we'll be left with 2a squared plus 1 square root plus c is equal to 0. Then when you bring this guy this side, we'll have c equal to moins ça. Okay, and this is going to be your value of c. So from here, you can just substitute your c there. You can substitute it as this here. It's going to be square root of 2a squared plus 1 exponential phi minus square root of 2a squared plus 1. Then from there, you can factor out the 2a squared plus 1 square root like that. And in the brackets, you have e phi, this e phi here. And this side is going to be a minus 1 left, which is what we have here as our s de phi. Questions? It's clear?
No.
You can explain where you introduced physical to omega t.
So you're not clear why we introduced phi is equal to omega t, or just do everything starting from there going down? Okay, so I said we're going to do this because we have to change the variable. In the question, they're asking us to calculate s de phi, but the expressions that we have up to this point are all expressed in terms of time, t. So we're going to have to change the variable from t to phi. So we need an expression that's linking phi and t. That's going to help us change the variable from t to phi. Okay, so that's where we got this. We calculated that phi was equal to omega t. And if I differentiate this side and I differentiate this side, I'm going to have d phi equal to omega dt, because omega is a constant there. So it's going to be d phi dt. Okay, de phi omega dt. Then from here, when I change the subject to a formula, I make dt subject. It's going to be dt is equal to de phi over omega. Okay, dt equal to de phi over omega by just dividing by omega on both sides of the equation. So it's going to be that. Then from here now, I can substitute wherever there's t, I can substitute with my new expression there. So first begin with here we have the s equal to the dt. So instead of writing dt, we'll substitute dt with its new value, which is the phi over omega. So it's going to be the s is equal to v fois d phi divisé par omega. And we know v is equal to this guy here, omega exponentielle omega t, racine de 2a carré plus 1. So we substitute v by its value there. We substitute there, it's going to be like that. This omega and this omega here are going to simplify. And then we know that omega t is equal to phi because we don't want to have t in our expression. We want to work with phi this time around. So wherever there's t, we're supposed to substitute it with phi. Find a way of substituting phi there. So omega t is equal to phi. So this one is just simple. We just put phi in place of omega t, because we know phi is equal to omega t. So we have exponential of phi being there. And our new expression is going to be square root of 2a squared plus 1 multiplied by the integral of exponential of phi. The exponential of phi is this one here, de phi. Why has this expression come to this side of the integral? Because it's a constant and we are not integrating it. It does not concern us for now. So we just take it out of the way to simplify our way so it does not confuse our integral and cause us to get wrong values. We can take it out of the integral because it's a constant and then just leave whatsoever is going to be integrated. And in this case, it's just the exponential of phi because it's the only one that's varying there in terms of phi. So we have exponential of phi de phi integral. And then when we integrate exponential of phi de phi, it's going to give us exponential of phi still because the derivative of ex dx is still ex. That means when you integrate it still, it's still going to give you the same value. That's the thing about exponential of the exponent of a certain variable. When you're integrating it with respect to the same variable that is being raised to, the derivative is the same. That means the integral is also going to be the same. So exponential of phi de phi is still going to give you exponential over phi. For this part, I told you guys that in mechanics, you're going to use a lot of calculus and trig. That's why I emphasize at the beginning that make sure you do calculus and trigonometry. If you've never done calculus before, make sure you do it. And if you're not so good at trigonometry also, make sure you do it because you're going to meet, this is just the beginning, you're going to do a lot of these things as you go on. Do they ever ask such in diagram form? Yes, they do. Next questions we'll be looking at, there will actually be diagrams there, so you need to interpret the diagram. Just that this question is, there's no need for a diagram on this question, but other questions have diagrams. So as I was saying, calculus and trigonometry, I emphasize, calculus and trigonometry, okay? The concepts from mechanics you'll be using, it's just perhaps at the beginning of the question, the rest of the calculations you'll be doing is just math, as you have seen. We're just simplifying expressions, deriving, integrating, and using trigonometry where possible. That's what it's about. So you have to know these two, calculus and trigonometry. If you don't know them, go and start learning them. Go to YouTube, get books, and learn them. Okay, so you integrate exponential of phi de phi. It's going to give you a phi. So a phi plus c. Yeah, a phi plus c. The constant of integration. Then we need to find the expression of c. We cannot leave this like this. What's c? We don't know what c is. So we need to find the expression for c. And normally how we get the expression for c is we use initial conditions. So they'll give you initial conditions like when phi is equal to 0, s of phi is equal to something, something. So you can use those conditions now to calculate the value of c. So we know that when phi is equal to 0, s of phi is equal to 0 also. So we get s of phi, we equate it to 0 when phi is equal to 0. And where there's phi, here exponential of phi, we'll put a 0. and exponential of 0 is equal to 1. So what's going to be left is the square root of 2a squared plus 1 plus c is equal to 0. Then from here, we can just change the subject, making c subject by bringing this term on the other side of the equation. C is going to be equal to minus square root of 2a squared plus 1. Okay, so now that we have our value of c, we can substitute it there. It's going to be square root of 2a squared plus 1 exponential of phi minus square root of 2a squared plus 1. So there we can substitute, sorry, not substitute, but factorize square root of 2a squared plus 1 because it's a common term here and here. So when we factor it out, as in this case here, what's going to be left in the brackets is this e phi minus the 1 that's going to remain there. And this becomes our final expression for Labsis Kevelin in terms of phi, or S the phi. This is your final expression like that. Is it clear now? Those that didn't say, those that said it's not clear. Hello? When I asked at first, say, is it clear? A number of you spoke out.
It's clear. It's clear.
Oh, it's clear. Good. So we go to the next question. The next question is saying, calculer le vecteur accélération. Okay, so vector acceleration. So I'm going to do to you guys what our woman did to us in our time. Okay, so what she did was she said the acceleration is equal to this, and you know how to calculate the acceleration is the formula is there, and you also have the formula for the acceleration for down the bars cylindric. Since we're still in the bars cylindric, these expressions are written in the bars cylindric. So you have the formula or the expression for the acceleration in your notes. So using that expression and using the expressions that we have for rho, for phi, for z, reproduce this thing here in the box. It's going to be a chance for you to practice this TD, you know. So use the techniques we used when calculating the v-test. Yeah, just use them and reproduce that there. It's very simple. It's a bit long, but it's very simple. It's just like the question we were doing yesterday, but that was even very complicated. This one is just going to be a matter of differentiation and simplification afterwards. It should be relatively easy for you guys. So you should try it out. You reproduce this expression there. This is the final expression for the acceleration. So you start from there and reproduce that.
And what is omega to power what?
It's omega squared. I'll send you guys this polycop, this pamphlet, or this PDF rather. After the class, I'll send it to you. So, question 4 is asking us to calculate the acceleration. Question 5 is saying exprimer l'accélération tangentielle. Again, this is just something that's in your notes. The formula for the acceleration tangentielle, again, you have them in your notes. So all these things, you have to know them by heart, you know. So accélération tangentielle is equal to dv dt suivant t. If you check your notes, the notes are here, just to show you proof that I'm not just saying they're in your notes without them being in your notes. It's here. It's here. This one here. Gamma t. Gamma t is this first one here. dv dt suivant t. Gamma t is equal to dv dt suivant t. So these expressions, you have them. You just know them by heart. You understand them, then you know them by heart, and you'll be able to use them. So gamma t is equal to this dv dt over t. So you get your module of v, you differentiate it par rapport au temps, you multiply it with your vector tangentiel, and you have your gamma t. Okay, so v, we have it up here. V is equal to this one. We've already calculated it. Omega exponentielle omega t racine de 2a carré plus 1. So we have our V there. We write it there. Derivé of the same expression V over t. Suivant t. Don't confuse the vector vitesse and module de la vitesse. Don't confuse the two. V with a flash on top of it is different from V without a flash. There are two different terms, as you have seen. So you might see dv dt here, and you use the vector vitesse, you get the wrong answer. This dv dt, the v here is the module of the vector vitesse. That's what you're using in this case. Okay, so it's the module, and it was that we've already calculated it. So when you differentiate this thing in the square root is a constant. Omega is also a constant with respect to time. So all we'll be differentiating is exponential omega t par rapport au temps. And when you're differentiating exponential omega t, it's going to give you omega exponential omega t. Okay, omega exponential omega t. So now we have two omegas there. So the omega times the omega is going to give us omega carré. That's why we have this omega carré exponential omega t with this constant here, there, the racine of 2a squared plus 1. Suivant t. We cannot leave it like this because we have the expression for t. We were just from calculating it. T, we found it as being equal to this. This is vector tangential. It's there. So we're going to substitute its value. We've already calculated that. We are going to substitute t with its value there. So you see this square root of 2a squared plus 1 and this square root of 2a squared plus 1 are going to simplify like that. They simplify. And what's going to be left is omega carré exponential omega t, and what's in the brackets there? This here. The a euro plus a e phi plus k. Okay? So for this one, the trick is just differentiating the module de la vitesse there, omega constant, the square root and its term there constant. So we're just left with exponential omega t. So we're going to derive exponential omega t dt. It's going to give us omega exponential omega t. And then the omega will square each other. So we'll have omega carré exponential omega t. And that's where this final expression is coming from. Is this one clear? Okay, someone says repeat. So from our notes here, just starting from here, gamma dt is being given by dv dt suivant t. Okay, now the v here we're using is not the vector vitesse, but the module de la vitesse. The module, not the vector vitesse itself, but its module. Sorry, not that. There now. So we need the expression for v, the module, which we had already calculated. We've already calculated all these things. So v is equal to omega exponentielle omega t fois la racine de 2a carré plus a, which is this here. We write it there. So since we're deriving v, we have la dérivée par rapport au temps de omega exponentielle omega t square root of 2a squared plus 1, like that there, suivant t. Then we are going to differentiate this term here that we have to differentiate. But when you look at this, omega is constant. From the question, they said omega is a positive constant. So omega is constant. And this one we know is constant because a is constant, 2 is constant, 1 is constant. So this in the square root is a constant term also. So we're not going to deal with them. What's going to concern us is just this one here, the exponential omega t, because it's not constant, it contains t. Exponential omega t. So now the derivative of exponential to the power omega t, we're going to derive the power there. I said when you're deriving exponential of a certain power, you first derive the power, then when you get the derivative of that power, you multiply that derivative by your entire expression. So we're going to derive the omega t here, which is the power, and the derivative of omega t par rapport à t is going to give us what? Omega, okay? So we're going to have omega multiplied by the entire expression. So when we multiply omega by this entire expression, it's going to become omega carré. And that's how come we have omega carré here, exponential omega t, multiplied by this same term also, which is a constant, suivant t, okay? Now, we have our expression for the vector tangent. We've already calculated it, this one here. We've calculated it. T is equal to that. T is equal to that. So we can substitute that expression for t here where there's t, and we'll have this here. And from here we see that square root of 2a squared plus 1 and square root of 2a squared plus 1 here are going to simplify each other, and they're going to cancel out like that. And what's going to be left is omega squared exponential of omega t multiplied by this term in the parentheses. And what's going to be left now is this omega t. Here we're just using the formulas that we have in our notes, the expressions that we've already found before. You substitute, you simplify, and you get your final answer. It's like this question is just trying to test how well you've understood your formulas, how you've, if you've mastered them or you've known them and you know how to use them and when to use them. That's what this exercise is about. It's also showing you exactly what you need to know. So you've seen now that you need to know vector position OM. You've seen you need to know vecteur vitesse. You need to know vecteur accélération dans tout le repère qu'on a fait jusqu'à maintenant. On a fait 4, cartésien, cylindrique, sphérique, and finite. So you have to know all 4. Okay? Is it clear? Okay, great. We are now going to do this final one, gamma n. So not the final one, but the next one. The question is saying déterminer l'accélération normale. So again, when you come to your notes, the same formula, you see gamma, the total gamma is equal to gamma t plus gamma n. Now notice something. If you want, you can use this formula here to calculate gamma n, but it's going to be hard for you because you don't know what the radius is, okay? But we have gamma t and we have gamma, the total gamma. So we can calculate gamma n by just changing the subject, by bringing gamma t this side. So it will be gamma n is equal to a gamma total, so to say, minus gamma tangentiel, which is what is being done here. Gamma de m, which is this one here, that I've asked you guys to reproduce in your free time, is equal to gamma tangentiel, which is this one here, plus gamma n, which we're being asked to find. So you make n subject is going to be gamma n is equal to gamma de m minus gamma t. Gamma de m is this one there, so you substitute it there, and gamma de t is this one here, you substitute it there, and then you simplify your work. When you simplify it, you'll find that you'll be getting this here. When you simplify this, you just get this and subtract this. Notice something. This outside the brackets, omega squared exponential omega t, is the same as this one here, okay? So it's from there, it's easy for you to simplify, okay? When you multiply, for example, I factor out in both of them the omega squared exponential omega t. So when I factor out the both of them, what's going to be left is a e rho plus a e phi plus k, then minus, because I have a minus here, minus 2a e phi plus k. So not plus, but minus k also, because I have a minus there. So the k and the minus k will simplify there. Then here I have plus a e phi, and here I have minus 2a e phi. So when I simplify that, it's going to give me a e phi. I'm going to be left with a e phi, and then the a euro is going to be maintained also, which is this one here, this expression there, a omega carré exponential omega t euro plus a omega carré exponential omega t e phi, because the k and the k will simplify there, and I'll be left with this. Then I can factor out the a omega carré exponential omega t. Then in the parentheses, I'm going to have euro plus e phi. as I told you guys in the other question, I'm reading out the solutions to you guys, and I'm reading them out. So it's a bit hard to make you guys see some of these things. It's better when someone is solving and just seeing. That's why I have told you that when you sit down with a pen and paper, and now you try to redo all these things, you try to simplify while writing them instead of just reading them out loud or having them read to you out loud. When you're working with a pen and paper, going step by step, some of these things will become clearer. So make sure you go through these things. You go through them afterwards, preferably tonight, because you forget. Tomorrow you wake up and then you'll be asking yourself, how did you do this? But today you are listening, your memory is still fresh. So in the night, you can sit down now alone with a pen and paper and try and redo these things step by step. They'll become clear. I'm reading them to you, so they're seeming like I'm telling you, you simplify, you do this and that. Just yourself, but how is it simplified to that there? But when you get a pen and paper, you just realize, this is how it's simplified to that. So on the show sum. Okay? So when you subtract this and this, you just subtract and you see it's going to give you that 2 simplement. Then now they're asking us to calculate on the jouer le rayon du courbure rosé. They're calling the rayon rosé. Okay? So you come to again, the formulas in you. So I'm telling you, this question is just testing your memory, to see if you know your formulas well and you're able to apply them. So they're asking us to find R, and we know that gamma n is equal to V squared, V is the module, over R, which they're asking us to find, R say, suivant n. So we're just going to get this formula here, gamma n, which is V squared over R say, suivant n, and it's the one we are going to work with. So gamma n is equal to V squared over rho c suivant n. But this time around, we won't use suivant n because we'll be working with the module. So we'll calculate the module of gamma n. As you can see here, there's no flesh on the gamma. It means you're working with the module. Okay, there's no flesh on the gamma. So it's the module. So module of gamma n, you can calculate. You just square this. Actually, it's just the same term because they are the same. It's the same thing for euro and phi. And when you're calculating the module, you just get the coefficients of these base vectors. You square them, you add them, and you square root them. So it's like you just be adding this plus that square root. This plus that square root. Yeah, so gamma n is equal to V squared over rho c. You change the subject to the formula, rho c is going to be equal to V squared over gamma n. V we have been working with V so much, sure you must know it by heart now. So V is this term here, the term there, V. When you square it, it's going to be omega squared exponential squared of omega t, and then this term with a square root, you square it, the square root is going to disappear. So you just have 2a squared plus 1 over the module of gamma n. You calculate the module of this term there. I'm sure you know how to calculate the module by now. So you expand it if you want. You first expand it. It's going to be r omega. It's r omega carré exponential omega t rho plus r omega carré exponential omega t. Then you get the coefficients of all the base vectors there. So the coefficient of rho is this one, r omega carré exponential omega t squared. You square it plus the coefficient of phi is r omega carré exponential omega t squared. Then you add the two of them. When you add them, you square root your answer. Okay, when you add them, it's going to give you 2a squared omega squared exponential squared omega t, or exponential of 2 omega t. So you can square, when square rooting, you can separate them. So square root of 2, because square root of 2 is a decimal, we won't work with it, we'll just leave it as square root of 2. Then you square root the other terms that are squared here, the a squared, the omega to the power 4, and the exponential of 2 omega t is going to be a omega squared exponential of omega t. It's going to go back to the way it was, and this is what we have here, a omega exponential omega t multiplied by the square root over 2. Then from here, you can simplify. So the omega squared and the omega squared will cancel out. Then here you have exponential of 2 omega t. Here you have exponential of omega t. So this one on the bottom is going to disappear. And then in the numerator, we're going to remain with 1 exponential because it's exponential 2 omega t. So now it's just going to be exponential omega t. And your final expression is going to be this, 2a squared plus 1 over square root of 2 and exponential of omega t, like that. It's just simplification. As I've told you guys, you get the formula, you apply it, then after that you simplify it. Is the expression for the radius clear? No? It's not Vn, it's gamma n. Yeah. Okay. So the R is staying. It's just R square root of 2. The R is not going anywhere. The omega squared is going to simplify with the omega squared in the numerator. There's omega squared in the numerator and omega squared in the denominator. And then you have exponential omega t in the denominator. And it's like in the numerator, we have exponential omega t squared. So the one in the denominator is going to disappear, and one of them in the numerator is going to cancel out also. So we're going to remain with exponential omega t. Then the 2a squared plus 1 is going to stay. So that's where it has come from, 2a squared plus 1 exponential omega t over a square root of 2. Yeah. These ones for simplification, as I've told you guys, reading them out to you is a bit confusing. They're better off when you're seeing someone solving and all. So when you try and solve them on a pen and paper, they'll be much, much clearer. Okay, then the last question of this exercise. Quelle est la trajectoire du point P quelle est la trajectoire du point P? La trajectoire. So, trajectoire de P de projection de M sur X ou Y. So we have these formulas first of all. X, that we've been looking for, X is equal to A exponential omega T cos omega T. Y is equal to A exponential omega T sinus omega T. Then, honor, we know cos squared omega T plus sin squared omega T is going to be equal to 1. Okay, so this implies that x squared, when you square this expression and you square this expression, you square the x and you square the y, and then you divide by these guys here. They are exponential omega t. It's just going to give you cos squared omega t and sin squared omega t. That's why this term is equal to 1 here, this term. It's like x squared over this. It's going to give you cos omega t squared. And y squared over this is going to give you sin squared omega t, which is equal to 1. Then when you express them as you find the common denominator, which is this guy, and then you bring this side, it's going to be x squared plus y squared is equal to a squared exponential of omega t. The way I understood this, okay, for this one, I'm even going to put a disclaimer. I'm not so sure how we really solve them. The woman did not explain it well to us, but from the way I interpreted it is that when you have something moving in a curve, you know, like here we're working with Les Abscisse curviligne, so it's like it's moving in a curve. So when it's moving in a curve, it's like there's a circle somewhere. It's like they're working in circles, you're working with circles. So when they ask you to find its trajectoire, you use the formula for the circle. You guys know the formula for the circle, not so? The formula for the circle and which is we usually use this this rule here, this one that you've seen, x squared over something plus y squared over something should be equal to something, something this side. It's mostly equal to the radius. Yeah, it's mostly equal to the radius. So you say x squared plus y squared is equal to what? At the end, you have to put the radius. But as I've told you guys, I'm not so sure also. So in case you do some research, which I would recommend you do, and find a better explanation, you can even share it with your friends. But for me, I just try to use my own logic there and try and understand and get me an answer that satisfied me. So it might be true, it might be correct. Also, it might be correct, it might be false. I've already told you guys. So x squared plus y squared is going to be equal to a squared exponential omega t. When you simplify this entire expression, it's going to give you that there. So what we're going to try and do now is try and introduce the radius on the right side of the equation, So they are telling us on peut avoir exponentielle de 2 oméga t égale à ça. This is coming from this thing here, this expression that we found for the radius there. When you make exponential omega t subject. So they're telling us on peut avoir exponentielle de 2 oméga t equal to that. From here, you make this subject, you make exponential omega t subject, and then you square it. It's going to give you that there. Then from here, you can substitute. You can substitute in this expression that we have here, x squared plus y squared equal to a squared exponential 2 omega t. You can substitute this expression that we have there, substitute it there, and then you simplify, and it's going to give you that there as your trajectoire. This is the formula for the circle. If you've got, not if you've got time, just Google it. Google the formula for the circle in case you don't know how you express it. Normally it's x squared plus y squared is equal to the radius squared. So this is going to express your trajectory. But as I told you guys again, I'm going to emphasize, this is my own logic. The woman didn't explain to us why she did that. She just did it and gave us, this is going to be a trajectory. So for me, I just figured that since we're dealing with a curve, okay, in part circles, so normally the trajectory is going to be derived from the formula of the circle. So even as we are working, just try to go to the formula of the circle where you have x squared plus y squared is equal to the radius squared, and that's going to be your answer. So when you look at this here, this is going to be like the formula for the circle you're working with, x squared plus y squared is equal to, this is going to be the radius of that circle. You'll be working with the trajectory for that point you are working with. I know this one is not so clear, but we can just leave it for now. Okay, so besides the last question, is it clear for exercise 3? Besides this last part for the trajectory.
Yeah, it's clear.
Okay, if it's clear, then we have 30 minutes to go. So we'll try and go quickly over this question, but it's a bit long also. It's written exercise 3, but it's not supposed to be exercise 3. Mais c'est pas grand chose. We still have it. So they're telling us soit R, OX, Y, Z un référentiel absolu. Now here we're dealing with changement de référentiel. The last part we did in our cours, changement de référentiel, we have two référentiels there. So soit R, OX, Y, Z un référentiel absolu dont le plan OX, Y. Une particule M est assujettie ou est subjected à se déplacer sur une tige spirale. So here, this tige here, there's a point M. The M is here. It's moving like that. Okay, it's moving like that. And we have OM being equal to A à la puissance A exponentielle phi E rho. A exponentielle phi E rho. And we have our phi. They've told us phi is the angle between I and E rho. So E rho is there and I is there. So phi is this angle between them there. Okay? Then we have une particule M0 se déplace dans le même plan. So M0 se déplace dans le même plan, somewhere there. And OM0 is equal to A E rho. So A E rho. Still here, still suivant E rho. So M0 is here and M is there. Okay? So you have M moving like that, being displaced like that. And you have M0 in the same plane, also M0 in this dotted line, moving like that. So it's like you have your M0 here and you have your M there. Then they told us soit R1 with center M0. So the center for M0 for R1 is here on M0 and it's with the base E rho, E phi and K. Le repère relatif. I explained this to you guys. Repère relatif, repère absolu. So repère absolu is R, O, X, Y, Z, this one here. And then we have un repère relatif. Like the repère relative is in movement with respect to the repère absolu. Yeah. And now we're going to try and do some workings, some calculations based off of the point M, the point M0, le repère R1 et le repère R. Okay, le repère absolu et le repère relatif. Changement de référentiel. So the first question is saying, calculer la vitesse du point M par rapport à R1. Quelle est la trajectoire de M dans R1? Vitesse de M dans R1. Okay, vitesse de M. So M is there. M is at this point there. And they're asking us to calculate la vitesse de M dans R1. So what's the origin of the repère R1? You ask yourself. They're asking to calculate vitesse de M dans R1. So normally what they're asking to calculate is the derivative of the vector position dans R1. Okay, so are we going to work with OM? Are we going to work with what? Is what you're supposed to ask yourself. So we're finding vector vitesse du point M dans R1. So you ask yourself, what's the origin of the repère R1? The origin has been given here as M0. R1 has origin M0. Whenever they give you a representation like this one, R1, and then there's M0, there's O, there's whatsoever, this is telling you the origin of that repère. So M0 is the origin of the repère R1. So the vector position du point M dans le repère R1 is going to be M0M, not OM. OM is dans le repère R because O is the origin of the repère R. But since we are working in R1 this time, we're going to use the origin dans le repère R1. And the origin there is M0. So your vector position becomes M0M and not OM. Careful. This is how you confuse things and lose marks. You are in R1. Okay, you are in R1. The origin there is M0. So when they ask you to find vector du point M dans R1, you won't be deriving OM. You'll be deriving M0M because M0 is the origin there. So now you need to find the expression for M0M, okay? We have OM and we have OM0. We use these two here, OM and OM0. They'll give us the expression for M0M. So they're telling us vector position de R1, say M0M, as I'm from explaining to you guys. Avec M0M, this time here, just subtracting vectors. It's like you go from M0 to OM, then from OM to M. You would have moved from M0 to M, from M0 to O, and from O to M. You will move from M0 to M. And then M0O. M0O is equal to what? You look at the question there. This is O, M0. But now we're dealing with M0O. So it's like the opposite. Same vector, but in the opposite direction. So you just add a minus. So it's going to be minus A, E, O, which is what we have here. Minus A, E, O. And then OM is going to be the same thing. So it's going to be A à la puissance E, sorry, A exponentielle de phi suivant E rho minus A suivant E rho. When you factor out what needs to be factored out, which is the A and the E rho, you will be left with A between parentheses E phi minus 1 suivant E rho. And this becomes your vector position. And you see how easy it is for you to mess up in mechanics. It's very simple because the moment you find your vector position, you can go on to get everything correct. Okay? But also, when you get the wrong vector position, you go on and get everything wrong because everything you're going to do from there onwards, you'll be working based off of that vector position you would have found. So it's important for you to understand the referential you're working with, what vector position you're going to use, what's its origin, it's in which bars, is the bars fixed, is what you understand all these concepts, and then you go on and do your calculations. So as you see, from here on, we just have to now differentiate M0M par rapport dans R1. Okay, we're differentiating dans R1. This time around, in the first question, we weren't considering in which repère we are differentiating in. We were just differentiating because we were just working with one repère. But this time around, we have deux repères. So we need to know in what we are differentiating what. How are we going to differentiate it? Are we using formidable? Are we not choosing formidable? Et tout ça. So, vitesse de M dans R1 égale la dérivée de M0M, which is what's been written here, A E phi moins A suivant euro dt dans R1. Okay, dans R1. So when you differentiate this, we'll use the product rule because we have E à la puissance phi varying, E à la puissance phi moins A, and we also have euro. Normally we derive euro, but we will see if we have the right to derive euro in this case. So when we derive E à la puissance phi, as I told you, when you're deriving exponential of a function, the x, you derive that function of x is going to give you f prime of x. Then you multiply that f prime of x by the entire expression. So your final derivative is going to be f prime of x multiplied by exponential of f of x. So here we have exponential of phi. And we're deriving this expression par rapport au temps. So we derive the phi first of all, par rapport au temps. It's going to give us phi point. So that phi point, you multiply it by the entire expression, is going to be phi point multiplied by l'exponentielle de E à la puissance phi, as you can see from here. Then this one is going to disappear because it's constant par rapport au temps. So it's going to be phi point E à la puissance phi suivant euro. And then we're going to keep this as a constant. Then we're going to derive euro. But you ask yourself, in which bars am I deriving euro? I'm deriving it dans quelle base, mais dans quel repère? I'm deriving it in the repère R1. So now you need to ask yourself, is euro moving with respect to R1? Is it moving with respect to itself? Because euro belongs to the base R1, okay? Euro, this one, euro, phi, and k. They are written in R1, okay? So is euro moving with respect to itself? No. So euro dans la base ou dans le repère plutôt R1, it's fixed. It's not moving with respect to itself. It's moving with respect to the repère R, le repère absolu. But with respect to itself, it's not moving. So it's fixed there and we're not going to derive it, okay? Or when we derive it, it's going to give us 0. it's a constant. So de euro dt is going to give us 0, and that's why we have de euro dt being equal to 0 there. It's going to cancel out. So it's as good as not deriving it. We just leave it. And our vitesse is going to be a phi point exponentielle de phi suivant e euro. C'est la vitesse relative. I know it's a bit too much for you guys at this point. I can just imagine your confusion. Maybe there's some of you that have understood it, alhamdulillah. But if you go through the notes and then you go through the TD again and again, it's going to be clearer, okay? Not even clearer, it's going to be clear, but you just need to know dans quel repère you are working in. If the repère is mobile with respect to the repère you're deriving in, or it's not fixed, it's mobile, you need to identify that, and then you continue with your calculations. It's these small things that count in mechanics. They can quite easily confuse you, okay? They can quite easily confuse you, but then again, if you understand them well, they just seem like, oh, simple stuff. I know it's fixed in this repère. I know it's mobile with respect to this repère, so I can differentiate it, etc. So we have found the expression for la vitesse du point M dans le repère R1, which we call la vitesse relative. As I told you guys when I was explaining changement de référentiel, la vitesse du point M dans la base ou dans le repère relative is the vitesse relative. And when you look at the vitesse is just some term, some coefficient suivant E rho. So when they ask you, what's the trajectoire? What's the trajectoire? You look at the vitesse. The vitesse is just some term suivant E rho. Not actually the vitesse, but the vector position. The vector position rather. You look at the vector position. The vector position is just some coefficient here suivant E rho. That means your vector is going in one direction, in a straight line in that direction. So when they ask you what's the trajectoire, you just tell them it's moving in a straight line following E rho, looking at the nature of the vector position. And that's the answer they have given you here. Trajectoire de M dans R1, on a M0M égale A, E phi moins A, suivant E rho. Okay, it's just some term which we call X suivant E rho. Seul non nul. Donc, la trajectoire de M dans R1 est une droite est une droite dans la direction de E rho. So that's like a line in the direction of E rho, because the vector position is just some coefficient, some value in the direction of E rho, and that becomes its trajectoire. It's just moving in a straight line in the direction of E rho. Is that clear?
I have a question.
Yes, yes.
This question, this exercise 4 is a bit confusing. How did you know that is it zero is fixed?
Because we are deriving it in R1, okay? It's like par rapport à R1. It's in the repère R1, okay? And euro belongs to the repère, the same repère R1. So it's like it's not moving. The base is not moving in R1. No, with respect to R1, it's not moving. It's moving with respect to la base absolue. Okay, in this question we have deux bases or deux repères rather. Okay, even base can work since we have EJK and we have euro, EFINK. So we have deux bases, R, O, X, Y, Z, un référentiel absolu. And then we have this one that's relative. Normally how the movement is that the repère relative moves around or with respect to this one, le repère absolu. Okay, this one relative moves with respect to to this repère absolu. So if we are deriving expressions in this repère relative with respect to this repère absolu, or in this repère absolu, we are going to treat them as mobile. The euro, the phi, not the car is fixed, the euro and the phi. We're going to treat them as mobile. They are moving with respect to this one. But when you're deriving them with respect to themselves, it's like it's not moving with respect to itself. When you look at the Earth, for example, the Earth is moving around the sun, okay? So meaning the distance of the Earth or the position of the Earth is changing around the sun with respect to the sun, it's changing. So if you're going to derive something on the Earth, maybe a coordinate on the Earth, that coordinate is not going to be moving with respect to the Earth, because the Earth is not moving with respect to itself. It's moving with respect to the sun. Its position is changing when you're looking at its position from the sun. But when you're looking at the Earth's position from the Earth, can you see the Earth moving? You, like for example, Ruben yourself, can you see the position of the Earth changing from where you are?
No.
You can't see it changing. So it's like the Earth is not moving with respect to itself, okay? Here on Earth, we cannot see its movement. So it's like it's not moving with respect to itself. But now, if you change the repère in which you're considering it from, now you look at it from the perspective of the sun. Now you can see its position changing. So in this case, the sun is going to be like our repère absolu, and the Earth is going to be our repère relative. It means when you're deriving it, when you're deriving le repère relative with respect to itself, it's not moving. It's fixed with respect to itself. But when you're deriving it with respect to the repère absolu, then it's going to become mobile because you can see it moving now. It's moving with respect to that repère absolu. So here we were deriving euro dans R1. So it's like euro is not moving in R1. It's not moving. It's fixed with respect to itself. But if we are to derive euro with respect to this one now, R, le repère absolu, now euro is going to become mobile. We'll see it move now. It's going to be moving with respect to that repère absolu. I don't know if you guys get the picture a little.
Yeah.
Okay. So it's clear on that one. Are there any other questions?
Yes, there is a question.
Yes, yes.
Can you just kindly repeat, starting from the trajectoire there? The
Trajectoire de M. Okay, the question is asking to say, what's the trajectoire of the point M dans R1? So the trajectoire du point M dans R1, first of all, you need the vector position. You use the vector position dans R1. The vector position in R1 is M0M. So what's the value of M0M? The value of M0M, which we found here, was A, between parentheses, E phi minus 1, suivant E rho. So it's like you have some term, some value, suivant E rho. So M in that point is just in the direction of one base vector, or one vector, which is E rho. So it's moving in a straight line because it's in that one direction. It's moving in a straight line in that one direction, E rho. It's like when you look at, let me take you back to this. Euro is this one here. We can look at it as this one down here. Okay. So when we have that answer that we have as A, E phi moins A suivant euro, we can say, for example, E phi moins A suivant euro is this value here, and then rho is going like that there. So it's like M is just moving in this direction there, suivant euro, just like that. It's just going like this. So when they ask you what's its trajectoire, it's moving in this straight line, in this direction of euro, according to the vector position that we have. It's just moving like that. Like that, in a straight line, suivant euro. Is it clear? FD.
Yes, yes.
Okay. More questions? Okay, good, 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 good. We go to the next one. Vector d'entraînement. Vector vitesse, sorry, vector vitesse d'entraînement. So, when you come here, changement de référentiel, this part. Even here, you just need to know these formulas. There's no need for you to start thinking vector vitesse d'entraînement is equal to what? No, it's equal to this. You try to derive the expressions to get the formulas. No, you can just know it par cœur and use it every time. Why did we write that? This one here. Vitesse d'entraînement. It's in your notes again. So, vector vitesse d'entraînement is equal to vitesse de O', but this case O' is just representing the origin of the repère or relative. It's not always going to be O', as in the question you have seen, we have M0. So O' is representing the origin of le repère or relative. So we have la vitesse de M0 dans le repère absolu R plus oméga, rotation de R', R vectoriel O', So here we have O', in our question is going to be M0, M. Because O' in that case is representing M0. So vector d'entraînement, we're going to use the same formula or from looking at, so you just have to know it. So vecteur vitesse d'entraînement égale vitesse de M0 dans R, la base R, sorry, le repère R plus rotation de R1 par rapport à R0 vectoriel M0, M. So we first start by calculating this one here, vitesse de M0 dans R. Okay, so vitesse de M0 dans R, we are going to use the vector position de M0 dans R. You're going to get the origin of the repère R, which is what? O, and the point which you're studying now, which is M0. So our vector position is going to be OM0. It's going to be d de OM0 dt par rapport à R. And OM0 is equal to, we have it in the question, OM0 is equal to A suivant E rho. A suivant E rho. Then you ask yourself, this time around, you are deriving in which repère? This time we're working in R, okay? So euro is no longer fixed. In the first question, it was fixed because we're working in R1, but this time around we're working in R, and R1 is mobile with respect to R because it's moving around R and also translating from R far from it and back to it, far from it and close to it. So you get the picture. So euro this time around is not going to be fixed. It's going to be mobile because we are working in R, le repère absolu. And alpha, sorry, not alpha, but A is a constant. So we can just take it out to the derivative. And we're going to derive d de E rho dt par rapport à R. Okay? And d de E rho dt par rapport à R, we already know what this one is. It's phi point E phi. We've been doing this for a while now. Deriving euro par rapport au temps, it's going to give us phi point E phi, and that's going to be your vitesse de M0 dans R. It's going to be A phi point suivant E phi. We keep it as that. Then, calcul de la rotation here. La rotation is going to be oméga de R. Oméga de R1 par rapport à R vectoriel M0, M. You have this formula in your notes. So unless stated otherwise, omega is usually equal to petit omega, le W, and suivant K. Okay, unless stated otherwise, unless they state say omega is equal to this, but if it's not stated, you work with that. So here in the question, they haven't stated what omega is. They haven't stated. So we are going to work with omega K. Omega, or I know I'm saying omega, maybe some of you are confused. This omega here that I'm circling is capital omega in the Greek alphabet. Then this omega here that looks like a W is small omega. So we read both of them as omega. So this one is used in a general formula, and then this one there is used more specifically in the case. That's what I'm telling you. Unless stated otherwise, unless they give you the value of omega, you are going to be using this omega here, this small omega, in the direction of K. Now, why is it in the direction of K? This is where you are going to visualize a little bit. You have seen, they were telling you that this, okay, both M0 and M, they are moving like that. They are moving like that. And what's been represented is the plan horizontal. There's also Z. In the question they've given us Z. Z, c'est le plan vertical. So in short, these points M are rotating around Z. If you can picture that, they're rotating like that. So it's like they're rotating around l'axe vertical, which is Z. Okay, that's why we are using omega K, because they're rotating around Z. Since they're rotating in the horizontal axis, so they're rotating around Z like that, Z. Z is, you can picture Z coming out of my PC or of your PC, wherever you're watching from. You can picture it as coming out from there, making the vertical axis. And if these guys are rotating like this in the horizontal axis, it means they are rotating around Z. So they're rotating around K. That's why we have omega K. So in other questions, you might have them rotating around X. You just have to spot the rotation. You try to imagine the rotation. Sometimes they rotate around X, sometimes they rotate around Y, sometimes rotate around je sais pas quoi. You have to try and identify it so you know in which direction your rotation is going to be. So because in our question there, they're rotating around K, we have omega K. And then when you look at the question again, I told you mechanics is about imagination also. So they've told you phi is equal to the angle between E and E rho. So phi is the angle between E and E rho. E rho is this one here, and E is this one there. So the angle phi is the angle there. So when the point M is rotating like that, which angle is changing according to you guys? When it's rotating like that, we know that phi is the angle there. So when this is moving like that, which angle is changing? Going once, twice, no one. The angle phi is there. The angle, this is phi, is the angle there. So when I have this guy here, euro, rotating like that, isn't the angle phi changing? Because when this line moves there, it's going to be here now. So the angle phi would have changed now, it's going to be there. When I move this, it now becomes parallel to J. The angle phi would have changed now, it's going to be 90 degrees. When I move this to here, when I rotate it to this point, the angle phi is going to change now, it's going to be there. So it's like phi is the angle that's changing. So when we introduce the notion of omega, omega being the angular vitesse, it's like you're studying the velocity of an angle, how much an angle is changing. So we're studying the angular vitesse of the angle phi, how much phi is changing with time, the rate of change of phi with time. Okay, so the angular vitesse there is going to be for the angle phi. Because it's hard for you to picture that. You can try and imagine now. So it's like M is rotating around K, and as it's rotating, the angle that's helping us take note of its position, of its changes in position, it's the angle phi, as it is going around K, of change of phi with respect to time. So it's just going to be phi point. So our omega in this case is going to be phi point, the rate of change of the angle phi with respect to time. I mentioned this last week. Omega is the angular vitesse. The angular vitesse. Omega is the angular vitesse. Sorry guys, just give me a second. My landlord is calling. Just give me a minute. Okay, I'm back. So I was telling you guys about the what was that? Angular vitesse. Yes, angular vitesse. So I'm sure you guys now have a bit of an idea on the angular vitesse. When we say omega, angular vitesse, it's the rate of change of the angle under question with respect to time. So as I was showing you from the question here, I was showing you from the question that we have this thing rotating around the z-axis, rotating like that. And since it's forming this angle phi with the x-axis, when it's rotating like that, it's the phi that's going to be changing. It's just an application of what we looked at. It's an application of what we looked at here. I was explaining to you guys that rho is rotating in the horizontal plane like that. It's rotating around the z-axis and it's forming this angle phi as it is rotating. So that question there is just an application. They've just gotten this horizontal plane. This horizontal plane is what they've just got, and they've given you a question out of it. So it's still the same concept. You have this rho, this rho, or this rho rotating around the z-axis like that, rotating, forming an angle phi. So it's like phi is changing in time. Okay, phi is changing with respect to time. At what rate is it changing? What's its velocity of change, you know? Its velocity as it is rotating around like that. So you're going to derive phi with respect to time for you to get its velocity. Okay, and now that's going to be the angular velocity or the vitesse angulaire with this one here, the omega. So we have E point K. K is because it's rotating around the Z. So don't always write K. Look at the diagram you've been given. Ask yourself, around what is this rotation being made? It's around Z. Okay, so I'll write K. And then at what speed is it rotating? The angular vitesse, the omega, it's equal to what? So now you look at the angle, you look at the angle that's changing, it's phi, you derive the angle, you get your phi point. So that means M0M. We have the expression for M0M as this one here, A, E phi moins A, suivant E rho. From here now, when you're doing when you're doing product vectorial, the constants, you just put them aside. You forget about them. You just deal with vectors. So here, this phi point is a scalar. Or did I say constant? I meant to say scalars. You forget about the scalars, you put them aside. So this phi point is a scalar. We can just put it aside. Then the A, E phi moins A is also a scalar. We can put it aside and we'll just deal with the two vectors there, which is K and E rho. So we have K vectorial E rho. Now this is where I explained to you the principle of the vector direct. I didn't give you a figure. I said you're going in the clockwise direction, so you have E rho vectorial E phi. It's going to give you something. Then E phi vectorial K is going to give you something. And then K vectorial E rho is going to give you something. I even told you that when you go in the reverse direction now, in the anti-clockwise direction, you will be going E rho vectorial K is going to give you some expressions I give you, not so. Yes, so K vectorial E rho is going to be equal to E phi from that figure I gave you that I do for you, E rho, E phi, K. You should know that one also. This is where you'll be applying it, and you'll be doing a lot of this, okay, because you'll be calculating the v-test acceleration a lot. I know these formulas contain le produit vectoriel. Yeah, so you'll be using that there. So it's just going to be K vectoriel E rho, and K vectoriel E rho from that small figure I gave you is going to give you E phi. So it's just going to be A phi point E, A phi point E phi moins A E phi, like that, and that becomes your rotation there. It's going to be this one. So for you to get your v-test d'entraînement, you are simply going to add this first part and this part here. You add and simplify. So when you add them and simplify them, this page is not clear, but it's the same page as the next one. I did not realize that. So when you add the first equation that we found and the second equation that we had, you add them and simplify them, you are going to get this expression there. And then they told us to further deduce the v-test absolute. And then from the formula we have in our notes, we know that v-test absolue, which is la vitesse du point M dans R égale la vitesse d'entraînement plus la vitesse relative. We have calculated both vitesse d'entraînement and vitesse relative. So vitesse absolue is just going to be equal to la vitesse relative that we found as this there, and la vitesse d'entraînement, which we have found as this there. When you add these two, they are going to give you la vitesse absolue, which is your answer there. If you want to find the vitesse absolute again, you can try and use this other method where you just get your vector position OM, and then you derive it in R. If you derive it in R, it's going to give you the same answer as what you have there. But it's better you just work with d'entraînement, then you work with d'entraînement, then you work with your vitesse relative and you get your answer. Because when you try to derive it directly, you need to use formula de bord and do that. But in this case, when you go with the formulas vitesse d'entraînement and vitesse relative, you won't need to use formula de bord because it was already used to get those formulas you'll be using dans la formule de la vitesse d'entraînement et la vitesse relative. They've already used formula de bord to get those guys. So for you, using the formulas, you won't need to do it. But if you're going to derive OM just directly in R to get your vitesse, you will need to use formula de bord, and you might confuse yourself somewhere there. So just use vitesse d'entraînement and vitesse relative. Just know the formulas for the vitesse d'entraînement. The formula is this one plus that one, and the vitesse relative is that there, and you get your answer. We'll end here for today. We'll continue in the next question tomorrow, or not tomorrow, next week. We'll do the remaining part and a little bit of exercise 5. Not a little bit, the whole exercise 5. So we have ended on exercise 2. We'll do exercise 3 next week. You guys can go and revise what we've done. Just try to go through the stuff. You'll realize how understandable they are and easy they are. Are there any questions up to this point? Questions? No questions? Ok. If there are no questions, je vous souhaite une bonne journée, une bonne semaine, un bon week-end. Et on se verra la semaine prochaine, le mercredi, which I think is going to be our last session together. There's a question somewhere there. Okay, thank you. You're welcome. So, au revoir.